66 million years ago, the dinosaurs vanished in a single catastrophic moment, and Earth became an empty stage. But what came next wasn't silence. It was an explosion of life so bizarre, so unexpected, that it rewrote the rules of evolution itself. This is the Cenozoic Era, the secret age that nobody talks about. Yet it's responsible for everything you see around you today. From horses the size of dogs to whales that walked on land. From a planet covered in tropical jungles to ice sheets 2 miles thick. This era transformed a dinosaur graveyard into the world you recognize. The Cenozoic isn't ancient history locked in stone. It's the ongoing story of how mammals, including us, seized control of an entire planet. And the most shocking part? We're still living in it right now, experiencing the latest chapter of an age that began in fire and has never truly ended. 66 million years ago, on what seemed like an ordinary day in the late Cretaceous period, the sky above the Yucatan Peninsula suddenly ignited with a light brighter than 1,000 suns. A mountain-sized asteroid, roughly 6 miles in diameter, was hurtling toward Earth at a speed of 45,000 miles per hour. In the final seconds before impact, it compressed the atmosphere so violently that the air itself became plasma. Then it struck. The impact released energy equivalent to 10 billion Hiroshima bombs detonating simultaneously. The asteroid punched through Earth's crust like a bullet through paper, creating a crater over 93 miles wide and 12 miles deep. Rock vaporized instantly, transforming into superheated gas that shot upward at velocities exceeding escape velocity. The shock wave rippled outward at hypersonic speeds, flattening everything within 1,000 miles. Trees, animals, mountains, nothing survived the initial blast zone. The ground itself liquefied, behaving like water as waves of molten rock surged across the landscape. But the immediate destruction was just the beginning. The impact ejected trillions of tons of vaporized rock, sulfur, and debris into the upper atmosphere. Some of this material reached space, hanging in orbit before raining back down as molten glass spherules. These tiny beads of superheated rock fell across the entire planet, igniting wildfires on every continent. Within hours, Earth was wrapped in flames. Forests that had stood for millions of years became ash. The sky turned red, then black, as smoke from continental-scale wildfires merged with impact debris to form a shroud that encircled the globe. The dinosaurs that survived the initial chaos, and there were some, faced a different kind of apocalypse. The impact had vaporized rock rich in sulfur, ejecting billions of tons of sulfur dioxide into the stratosphere. This sulfur combined with water vapor to form sulfuric acid aerosols that blocked out the sun. Within weeks, global temperatures plummeted. Scientists estimate that surface temperatures dropped by 50 degrees Fahrenheit in some regions. This wasn't a nuclear winter. It was an impact winter, and it lasted for years. Photosynthesis, the foundation of nearly all life on Earth, ground to a halt. Plants withered and died in the darkness. Herbivorous dinosaurs, already stressed by the collapse of their food sources, began to starve. The massive sauropods that had dominated ecosystems for over 100 million years couldn't find enough vegetation to sustain their enormous bodies. Hadrosaurs, ceratopsians, and ankylosaurs followed. As the herbivores died, the carnivores that depended on them faced their own extinction. Tyrannosaurus rex, the apex predator of the late Cretaceous, couldn't adapt to a world without prey. The food chain didn't just break, it shattered completely. In the oceans, the situation was equally catastrophic. Plankton, The microscopic organisms that formed the base of marine food webs died en masse when sunlight disappeared. Without plankton, small fish starved. Without small fish, larger predators followed. The massive marine reptiles, mosasaurs, plesiosaurs, and sea turtles the size of cars, vanished from the fossil record. Ammonites, spiral-shelled cephalopods that had survived multiple extinction events over 300 million years, finally met their end. The oceans became graveyards, their floors carpeted with the shells and bones of species that would never return. Yet somehow, life persisted. While 75% of all species on Earth went extinct, that means 25% survived. But what survived, and why? The answer reveals one of evolution's most profound truths. It's not the strongest or the largest that endure. It's the most adaptable. Small mammals that could burrow underground escaped the worst of the fires and temperature extremes. Birds, the only surviving dinosaur lineage, could migrate to find food and shelter. Crocodilians, with their slow metabolisms and ability to go months without eating, weathered the famine. Freshwater fish, insulated from the ocean's collapse, survived in rivers and lakes. These weren't the dominant species of the Cretaceous. They were the underdogs, the organisms living in the shadows of giants. The survivors emerged into a world transformed beyond recognition. Forests were gone, replaced by landscapes of ash and charred stumps. The air was thick with particulates that turned the sky a perpetual twilight gray. Acid rain, generated by the sulfur aerosols, poisoned rivers and lakes. The climate swung wildly between extremes as the planet's heat regulation system struggled to stabilize. This was Earth at its most vulnerable, a wounded planet trying to heal from a cosmic catastrophe. But within this devastation lay the seeds of something extraordinary. The extinction of the dinosaurs didn't just remove the dominant animals, it removed the competition. For 165 million years, dinosaurs had occupied nearly every ecological niche on land. They were the herbivores, the carnivores, the scavengers, and everything in between. Mammals, which had existed alongside dinosaurs since the Triassic period over 200 million years earlier, had been confined to small, shrew-like forms that hunted insects at night. They were prisoners of evolutionary circumstance, unable to compete with the dinosaurs' superior size and efficiency. Now, suddenly, the prison doors were open. The ecological niches that had been locked away for millions of years were vacant. There were no massive herbivores to dominate the plains, no apex predators to control the food chain, no flying reptiles to rule the skies. At least, not the pterosaurs that had soared for 150 million years. This was an evolutionary blank slate, and the survivors would rewrite the story of life on Earth. The first million years after the impact were dark and chaotic, but they were also a period of rapid change. Plants began to reclaim the scorched earth. Ferns, which reproduce through spores rather than seeds, were among the first to return. Scientists have found a fern spike in the geological record, a thin layer of rock dominated by fern fossils, marking this transitional period. These weren't the forests of the Cretaceous, but they were a start. As plants returned, herbivores followed, and with herbivores came carnivores. The ecological pyramid began to rebuild itself from the ground up. What makes the KPG extinction so pivotal isn't just what it destroyed, it's what it created. This wasn't merely the end of the age of dinosaurs. It was the beginning of the age of mammals, the Cenozoic Era. The survivors of that catastrophic day would evolve into forms more diverse and bizarre than anything the Mesozoic had produced. Mammals would grow to sizes that rivaled the largest dinosaurs. They would return to the oceans and evolve into whales. They would take to the skies and become bats. They would develop intelligence, culture, and eventually the ability to contemplate their own origins. The asteroid that struck the Yucatan wasn't just a rock falling from space. It was a cosmic reset button, a random event that redirected the entire trajectory of life on Earth. If that asteroid had missed, dinosaurs might still dominate the planet today. Mammals might still be small, nocturnal creatures hiding in burrows. Humans would never have evolved. Every city, every artwork, every scientific discovery, none of it would exist. Our entire existence hinges on a moment of destruction so complete that it seemed like the end of the world. But it wasn't the end. It was a violent, fiery beginning. And what came next would be even more incredible than what came before. The Paleocene epoch, spanning from 66 million to 56 million years ago, was Earth's recovery room. A 10 million year period of healing, experimentation, and evolutionary chaos. Imagine walking through this world just a few 100,000 years after the asteroid impact. The skies have cleared, but the landscape looks alien. Where towering forests once stood, low, scrubby, vegetation now dominates. The air feels different, warmer, more humid, thick with the smell of decay and new growth. And everywhere you look, life is trying to figure out what comes next. The first thing you'd notice is the silence, or rather, the absence of what should be there. No thundering footsteps of sauropods, no bellowing calls of hadrosaurs. The sonic landscape of the Cretaceous, the sounds that had echoed across Earth for over 100 million years, was gone forever. In its place came new voices, the chittering of early mammals, the calls of surviving birds, the rustling of small creatures moving through underbrush. These weren't the sounds of dominance. They were the sounds of survival, of species tentatively exploring a world without overlords. The survivors of the extinction faced a planet that was simultaneously depleted and brimming with opportunity. The impact winter had ended, but its effects lingered in the soil, the water, and the very chemistry of the atmosphere. Carbon dioxide levels had spiked from the vaporization of carbonate rocks and the burning of forests, trapping heat and pushing the planet toward a greenhouse climate. Over the next few million years, global temperatures would climb well above pre-impact levels. The polar regions, which had been cool but ice-free in the late Cretaceous, became warm enough to support palm trees and crocodiles. Antarctica wasn't a frozen wasteland. It was a temperate paradise where forests thrived and mammals wandered through landscapes that would later be buried under miles of ice. This warming trend created ideal conditions for plants to reclaim the continents. After the initial fern spike, flowering plants, angiosperms, began their explosive diversification. These weren't the same species that had existed before the impact. Evolution was moving fast, testing new forms, new strategies, new ways to survive. Trees grew rapidly in the warm, CO2-rich atmosphere, creating dense forests that looked superficially similar to Cretaceous ecosystems but were fundamentally different. The dominant plant families had shifted. New types of palms, broad-leaved evergreens, and early versions of modern tropical plants spread across the continents. These forests were humid, swampy places where rainfall was abundant and temperatures rarely dropped below comfortable levels. Into these recovering ecosystems came the mammals, and they wasted no time filling the void left by the dinosaurs. For over 160 million years, mammals had been constrained by evolutionary pressure from dinosaurs. The largest Cretaceous mammals were about the size of a badger, impressive for the time, but hardly threatening to dinosaurs. Most were nocturnal insectivores with tiny brains and simple social structures. They had survived not by competing with dinosaurs, but by avoiding them entirely, carving out niches in the darkness and underground where large reptiles couldn't follow. But now, in the early Paleocene, something remarkable began to happen. Mammals started to grow. Within just a few million years, a blink of an eye in geological terms, mammal species appeared that weighed as much as large dogs. By the end of the Paleocene, some had reached the size of bears. This wasn't just growth for growth's sake. Size meant access to new food sources, better defense against predators, and the ability to regulate body temperature more efficiently. In a world without large predatory dinosaurs, there was no evolutionary penalty for growing bigger. In fact, there were advantages. The early Paleocene mammals were bizarre by modern standards. Purgatorius, one of the earliest primates, scurried through tree branches eating insects and fruit. It looked more like a squirrel than anything we'd recognize as a primate ancestor, but it carried within its genome the seeds of humanity's future. Pantalambda, a sheep-sized herbivore, lumbered through forests with a body plan that seemed confused, part bear, part hippo, with teeth that suggested a diet of tough vegetation. These early mammals were evolutionary experiments, protoforms testing body designs that would later be refined or abandoned entirely. The carnivores of the Paleocene were equally strange. Without large prey to hunt, early carnivorous mammals remained relatively small. Creatures like Criacus resembled weasels or small cats, hunting the abundant small mammals and birds that filled the undergrowth. But some species took a different path. The creodonts, an extinct group of carnivorous mammals, began to evolve larger forms. These weren't the sleek, efficient predators that would come later. They were heavy-bodied, small-brained animals with powerful jaws but limited intelligence. Evolution was still figuring out how to build a mammalian apex predator. One of the most fascinating aspects of Paleocene recovery was the speed at which ecological complexity returned. You might expect that after losing 3/4 of all species, Earth's ecosystems would remain simple for millions of years. But the fossil record tells a different story. Within 2 million years of the extinction, just 2 million years, ecosystems had rebounded to levels of complexity approaching those of the late Cretaceous. Food webs were reestablished, predator-prey relationships stabilized, herbivores developed strategies to process tough plant material, carnivores developed strategies to catch them. The fundamental structure of terrestrial ecosystems, producers, consumers, decomposers, reassembled itself with stunning rapidity. This rapid recovery reveals something profound about life's resilience. Evolution doesn't require millions of years to create complexity when opportunity is abundant. Given empty niches and available energy, life diversifies explosively. The Paleocene wasn't a slow crawl back to normalcy. It was a sprint, an evolutionary arms race where every lineage was competing to claim territory in a reorganized world. Species that evolved faster, adapted better, or got lucky with their traits thrived. Those that couldn't keep pace vanished, adding to the extinction toll. The oceans were also rebounding, though more slowly than the land. Marine ecosystems had been devastated by the extinction, particularly in the upper water column, where photosynthetic plankton had died en masse. But within a million years, plankton populations had recovered, and with them came the fish that fed on them. New species of sharks appeared, including some that grew to enormous sizes. Bony fish diversified into forms that would become familiar to us. Early versions of tuna, swordfish, and other pelagic predators. The oceans were still missing their largest inhabitants. The marine reptiles were gone forever, but life was filling the gaps in creative ways. Perhaps most intriguingly, some mammals began looking toward the water. The ancestors of modern whales were still landlocked in the Paleocene, but the evolutionary trajectory that would lead them to the oceans was already beginning. Small, semi-aquatic mammals started spending more time in rivers and coastal areas, feeding on fish and avoiding land-based predators. These weren't whales yet. They had legs, fur, and looked more like otters, but they were taking the first steps on a journey that would transform them into the largest animals ever to exist on Earth. The climate of the Paleocene was generally stable, but trending warmer. The greenhouse effect from elevated CO2 levels was pushing global temperatures upward, creating tropical conditions across much of the planet. There was no ice at the poles. Sea levels were high, flooding low-lying continental areas and creating shallow seas that teemed with life. Weather patterns were different from anything in the modern world. Less seasonal variation, more consistent rainfall, and a more even distribution of heat from equator to poles. It was a planet that would seem paradisiacal to someone from our cooler, more variable modern climate. But this stability was deceptive. Beneath the surface, geological forces were building toward events that would shake the planet once again. Volcanic activity was increasing as tectonic plates shifted and new ocean basins formed. The Atlantic Ocean was widening as North America and Europe drifted apart. India was racing northward on a collision course with Asia, a journey that would eventually create the Himalayas and permanently alter global climate patterns. These processes were slow by human standards, millimeters per year, but they were inexorable, and their effects would reshape the world. By the end of the Paleocene, Earth had transformed from a devastated wasteland into a thriving, complex biosphere. Mammals had established themselves as the dominant large animals on land. Birds had diversified into countless forms, from tiny insectivores to large flightless predators that terrorized smaller mammals. Reptiles, though diminished from their Mesozoic glory, still held significant ecological roles. Crocodilians ruled rivers and swamps, snakes had become efficient predators, and lizards filled countless insect-eating niches. The planet was alive again, humming with energy and evolutionary potential. But the Paleocene was just the opening act. What came next, the Eocene epoch, would take this warm, stable world and push it to extremes that would test life's resilience once again. The Earth was about to get hotter, stranger, and more alien than anything the Paleocene survivors had experienced. And in that heat, in that chaos, evolution would create some of the most bizarre and magnificent creatures ever to walk the planet. The recovery was over. The real story of the Cenozoic was about to begin. 56 million years ago, something went catastrophically wrong with Earth's climate. Over the course of just a few thousand years, perhaps as little as a few centuries, global temperatures spiked by 5 to 8 degrees Celsius. This might not sound dramatic, but to put it in perspective, the difference between our modern world and the last ice age is only about 5 degrees. What happened at the boundary between the Paleocene and Eocene epochs was one of the most abrupt and severe climate change events in Earth's history, and scientists call it the Paleocene-Eocene thermal maximum, or PETM. This wasn't just a warm period. It was a planetary fever, and it rewrote the rules of life on Earth. The evidence for the PETM is written in ocean sediments around the world. When scientists drill cores from the seafloor and analyze the chemistry of ancient shells and organic matter, they find a distinct anomaly at the Paleocene-Eocene boundary. Carbon isotope ratios shift dramatically, indicating a massive release of carbon into the atmosphere and oceans. Oxygen isotope ratios show that ocean temperatures increased by 4 to 5 degrees Celsius, even in the deep sea, where temperature changes are usually minimal. Shallow tropical waters may have reached 35 degrees Celsius, as warm as a hot tub, and approaching the upper limits of what most marine life can tolerate. But where did all this carbon come from? That's one of the great mysteries of paleoclimate science, and the answer likely involves a cascade of interconnected events. The most widely accepted hypothesis involves methane hydrates, ice-like compounds that trap methane molecules in a cage of water ice. These hydrates are stable only under specific conditions of cold temperature and high pressure, and vast quantities of them exist today in ocean sediments and permafrost. When ocean temperatures rose past a certain threshold, these hydrates began to destabilize, releasing methane into the water and atmosphere. Methane is a greenhouse gas 25 times more potent than carbon dioxide over a century-long timescale, and this massive release would have triggered runaway warming. But the methane release needed an initial trigger, and that trigger was probably volcanic. During the late Paleocene, the North Atlantic was tearing apart as Europe and Greenland separated from North America. This rifting produced massive volcanic eruptions that released enormous quantities of carbon dioxide and heated the surrounding ocean. As temperatures rose, methane hydrates destabilized, amplifying the warming in a vicious feedback loop. It was a 1-2 punch, volcanic CO2 followed by a methane bomb, that pushed the planet into a hothouse state unlike anything in millions of years. The effects on life were immediate and profound. In the oceans, the warming caused a massive extinction of deep-sea organisms, particularly foraminifera, tiny shelled protozoans that are crucial indicators of ocean health. These creatures couldn't adapt quickly enough to the temperature increase and the changes in ocean chemistry that came with it. The oceans became more acidic as they absorbed atmospheric CO2, making it harder for organisms to build calcium carbonate shells. Coral reefs collapsed in many regions. The ocean's circulation patterns changed as the temperature gradient between the equator and poles weakened, reducing the efficiency of the currents that distribute heat and nutrients around the globe. On land, the warming drove dramatic shifts in vegetation and animal distributions. Species that had been confined to tropical regions migrated poleward following the heat. Fossils of tropical plants have been found in Arctic Canada and Siberia, regions that are frozen tundra today, but were swampy forests during the PETM. Palm trees grew in Wyoming. Crocodilians swam in rivers at latitudes where polar bears now hunt. The entire planetary temperature gradient shifted, creating tropical conditions across more than half of Earth's land surface. For mammals, the PETM was both a crisis and an opportunity. Many species went extinct as their habitats shifted or disappeared, but others thrived in the new conditions. The fossil record shows a dramatic size change in many mammalian lineages during this period. Horses, which had been small dog-sized creatures called Hyracotherium, underwent a strange transformation. They actually got smaller during the PETM, shrinking to the size of house cats. This phenomenon, called dwarfing, is a common evolutionary response to heat stress and nutritional challenges. Smaller bodies are more efficient at dissipating heat and require less food to maintain, providing a survival advantage during climate extremes. But while some mammals shrank, others seized the opportunity to expand. Primates, which had appeared in the Paleocene as small, squirrel-like creatures, diversified explosively during the PTM. The warm, wet conditions created dense tropical forests that stretched from pole to pole, providing ideal habitat for tree-dwelling species. Early primates like tailhardina dispersed across the northern continents, island hopping across land bridges that connected North America, Greenland, and Europe when sea levels dropped during brief cooling intervals. These weren't the intelligent, large-brained primates that would come later. They were tiny, lemur-like animals with forward-facing eyes and grasping hands, adaptations for living in three-dimensional forest environments. But they carried within their DNA the potential for something extraordinary. The PETM also saw the appearance of new mammalian groups that would come to dominate later epochs. The perissodactyls, odd-toed ungulates that include horses, rhinos, and tapirs, made their first appearance during this time. So did the artiodactyls, even-toed ungulates that would eventually give rise to deer, pigs, camels, and cattle. These early ungulates were small and generalized, without the specialized teeth and digestive systems that would later allow them to process tough grasses. But they represented a new approach to herbivory, one that would prove incredibly successful as the Cenozoic progressed. The heat also triggered changes in vegetation that would have long-lasting consequences. Plants responded to the elevated CO2 levels with increased growth rates, but the warming also increased evaporation and altered precipitation patterns. Some regions became wetter, supporting lush rainforests. Others became more arid, creating the first hints of the drylands that would expand dramatically in later epochs. Plant communities reorganized themselves along new climate gradients, with species migrating poleward or to higher elevations to track suitable conditions. Those that couldn't migrate fast enough went extinct. The PTM lasted for approximately 150,000 to 200,000 years before Earth's climate system gradually brought temperatures back down. The recovery was driven by several factors. Weathering of silicate rocks accelerated in the hot, wet conditions, pulling CO2 out of the atmosphere and locking it away as carbonate minerals. The increased burial of organic matter in ocean sediments and peat swamps also removed carbon from the active carbon cycle. Slowly, like a fever breaking, the planet cooled. Temperatures declined. Carbon isotope ratios returned to normal, and ocean circulation patterns stabilized. But Earth didn't return to Paleocene conditions. The PETM had pushed the planet into a new climate state, the Eocene proper, which would remain hot but more stable than the thermal maximum. The early to middle Eocene, from about 56 to 40 million years ago, was a time of peak Cenozoic warmth. This was the hothouse Earth at its most extreme. There was no ice anywhere on the planet. Global temperatures were 12 to 14 degrees Celsius warmer than today. The Arctic Ocean was 20 degrees Celsius, warm enough for comfortable swimming. Alligators lived near the North Pole. Atmospheric CO2 levels were at least 3 to 4 times higher than pre-industrial levels, possibly much higher. This was a fundamentally different planet from the one we inhabit, a world that challenges our assumptions about what Earth's climate can be. In this hothouse world, life flourished with astonishing diversity. The forests of the Eocene were unlike anything that exists today. They were multi-layered, dense jungles where trees reached heights of 150 feet or more, creating closed canopy systems that blocked most sunlight from reaching the forest floor. The undergrowth was thick with ferns, vines, and flowering plants. The air was heavy with moisture and the sounds of countless insects, birds, and mammals. Walking through an Eocene forest would feel like being inside a living cathedral. Dark, humid, and teeming with life at every level. Mammals continued their diversification at a breakneck pace. The first true carnivores appeared during the Eocene, representing a major evolutionary innovation. These early carnivorans, ancestors of modern cats, dogs, bears, and weasels, had specialized shearing teeth called carnassials that allowed them to process meat more efficiently than the creodonts that had dominated Paleocene ecosystems. This gave them a competitive advantage that would eventually drive the creodonts to extinction. The evolution of true carnivores set the stage for the predator-prey dynamics that would shape mammalian evolution for the rest of the Cenozoic. The oceans, too, were changing in profound ways. Whales, which had begun their transition to aquatic life in the Paleocene, were now fully committed to the water. By the Middle Eocene, species like Basilosaurus stretched 60 feet long, with serpentine bodies, powerful tails, and vestigial hind legs, evolutionary leftovers from their terrestrial ancestors. These were the ocean's new apex predators, filling the niche left empty by the marine reptiles 20 million years earlier. Sharks also reached enormous sizes, with Otodus obliquus growing to 30 feet or more, patrolling warm seas in search of prey. The extreme warmth of the Eocene couldn't last forever. Climate systems have built-in feedbacks that eventually stabilize conditions, and by the late Eocene, around 40 million years ago, the planet began a long, slow cooling trend that would dominate the rest of the Cenozoic. The reasons for this cooling are complex and still debated, but they involve changes in ocean circulation, the positions of continents, and the gradual drawdown of atmospheric CO2 through weathering and organic burial. The age of extremes was coming to an end, but its legacy would shape everything that followed. For 165 million years, dinosaurs had held the title of Earth's largest land animals. Argentinosaurus stretched over 100 feet long and weighed perhaps 100 tons. Patagodon rivaled it in size, with thigh bones taller than a human. These were the giants of the Mesozoic, creatures so massive they defied imagination. When they vanished, it seemed impossible that anything could ever match their scale. But evolution had other plans. During the Eocene and Oligocene epochs, mammals grew to sizes that equaled and sometimes exceeded their dinosaurian predecessors, proving that the age of giants was far from over. It was just entering a new chapter. The story of mammalian gigantism begins with a simple question: why get big? Size comes with obvious advantages: defense against predators, access to high vegetation, better temperature regulation, and increased reproductive success. But it also comes with costs. Large animals need enormous amounts of food. They reproduce slowly, and they're vulnerable to environmental changes. For dinosaurs, the benefits had outweighed the costs for millions of years. For mammals, the equation was more complicated. Mammalian metabolism runs hot. We maintain constant body temperatures by burning calories continuously. This requires more food than the cold-blooded metabolism of reptiles. Growing large as a mammal means committing to a lifestyle of constant eating. And that's only possible in environments with abundant, reliable food sources. The Eocene provided exactly those conditions. The hothouse climate created year-round growing seasons across most of the planet. Tropical and subtropical forests stretched from the equator to the Arctic Circle, producing massive quantities of vegetation. Rivers and swamps were filled with aquatic plants. There was food everywhere, and mammals evolved to exploit it. The first truly large herbivorous mammals appeared during the Middle Eocene, and they were bizarre beyond belief. These weren't just scaled-up versions of smaller mammals. They were evolutionary experiments, testing body plans and ecological strategies that had never existed before. Consider Uintatherium, a creature that roamed North America during the Middle Eocene around 45 million years ago. This animal was roughly the size of a large rhinoceros, standing 6 feet tall at the shoulder and weighing over 2 tons. But it looked like something assembled from spare parts. It had a massive, heavily built body supported by thick, columnar legs. Its skull was adorned with 6 bony protrusions, 2 on the nose, 2 above the eyes, and 2 at the back, giving it an appearance unlike any modern animal. The purpose of these horns remains debated. Were they used in combat between males? For display? For defense? We may never know for certain, but their presence suggests complex social behaviors and possibly intense competition for mates. Even stranger were Uintatherium's teeth. Males possessed massive downward-pointing canines that extended well below the jawline. These saber-like teeth were too long to be used for eating and would have been formidable weapons in fights with rivals or predators. The molars, by contrast, were relatively simple and designed for processing soft vegetation. Uintatherium wasn't browsing on tough grasses or woody plants. It was eating soft leaves, fruits, and aquatic vegetation in the lush forests and swamps where it lived. This animal represented one of evolution's early attempts at creating a large, specialized herbivore. And while the Uintatheres would eventually go extinct, without leaving descendants, they demonstrated that mammals could achieve dinosaur-like sizes. But Uintatherium was only the beginning. During the Oligocene epoch, from about 34 to 23 million years ago, mammals reached sizes that truly rivaled the largest dinosaurs. The champion of Cenozoic gigantism was Paraceratherium, a creature so enormous that standing beside it would be like standing next to a 2-story building. This animal, which lived in Asia during the Oligocene, was the largest land mammal ever to exist. It stood 18 feet tall at the shoulder, taller than most modern giraffes. From nose to tail, it stretched 26 feet. Conservative estimates place its weight at 15 to 20 tons, though some researchers suggest it could have weighed up to 30 tons, approaching the mass of the largest sauropod dinosaurs. Paraceratherium was a perissodactyl, a distant relative of modern rhinoceroses, though it looked nothing like them. It had a long neck, somewhat like a giraffe, which allowed it to reach vegetation high in trees. Its legs were pillar-like, designed to support its tremendous weight. The skull was relatively small compared to the body, with a long, flexible upper lip that could grasp branches and strip leaves. Unlike modern rhinos, it had no horns. When you're that large, you don't need additional weapons. Size itself is the ultimate defense. The lifestyle of Paraceratherium was probably similar to modern elephants. It would have spent most of its day eating, consuming hundreds of pounds of leaves, fruits, and soft vegetation to fuel its massive body. It likely lived in family groups or small herds, using forests and woodlands where food was abundant. Its long legs and neck gave it access to resources that smaller herbivores couldn't reach, allowing it to avoid direct competition. The environment it inhabited was changing. The Oligocene was cooler and drier than the Eocene, with forests giving way to more open woodlands. Paraceratherium's body plan was perfectly adapted to this transitional landscape. In South America, isolated from other continents for most of the Cenozoic, mammals were evolving their own unique forms of gigantism. The most spectacular of these were the notungulates, a diverse group of herbivorous mammals found nowhere else on Earth. During the Oligocene and Miocene, some notungulates grew to hippo-like sizes, with massive bodies, short legs, and skulls adapted for processing tough vegetation. Toxodon, which survived into the Pleistocene, weighed over a ton and looked like a bizarre cross between a rhino and a capybara. These animals filled ecological roles similar to ungulates on other continents, but they did so with completely different evolutionary solutions. South America also produced the largest predatory mammal ever documented, though not during the same period as the largest herbivores, which would have made for spectacular confrontations. During the Miocene epoch, a creature called Argentavis magnificens ruled South American skies. This wasn't technically a mammal. It was a bird, a member of the pterotorn family, but its size deserves mention in any discussion of Cenozoic giants. With a wingspan of 23 feet and weighing up to 150 pounds, Argentavis was more like a small airplane than a bird. It probably couldn't flap its wings continuously and instead soared on thermal currents, using its massive size to dominate other scavengers at carcasses. The sight of this creature descending from the sky must have been terrifying to smaller animals. Back in the northern hemisphere, other lineages were experimenting with size. The Brontotheres, relatives of horses and rhinos, grew to enormous proportions during the Eocene. Megacerops, one of the last and largest Brontotheres, stood 8 feet tall at the shoulder and weighed 2 to 3 tons. It had a distinctive Y-shaped horn on its nose, probably used in shoving matches with rivals. These animals looked superficially like rhinos, but were adapted to eating soft forest vegetation rather than tough grasses. When climate change reduced their preferred habitats during the Oligocene, the Brontotheres went extinct, unable to adapt quickly enough to the changing world. The evolution of mammalian giants wasn't limited to herbivores. Predators grew large as well, though they never achieved the multi-ton masses of the largest herbivores. The reasoning is straightforward. Carnivores need to be mobile enough to hunt, which places practical limits on size. During the Oligocene, entelodonts, sometimes called hell pigs, became apex predators in parts of North America, Europe, and Asia. These animals weren't actually pigs, despite their name, but rather a distinct family of omnivorous mammals. The largest species, like Daeodon, stood 6 feet tall at the shoulder and weighed up to 1,000 pounds. They had massive heads with powerful jaws, capable of crushing bones and processing almost any type of food. Fossil evidence suggests they were both hunters and scavengers, willing to take on prey as large as themselves when opportunity arose. Perhaps the most fascinating aspect of Cenozoic gigantism is how many different lineages independently evolved large body sizes. This wasn't a single evolutionary event, but rather a pattern that repeated across different continents, different time periods, and different mammalian groups. Elephants evolved from pig-sized ancestors into the massive proboscideans we know today. Rhinos descended from much smaller forms. Even rodents got in on the action. During the Pliocene, South America was home to Joseph Ortegasia, a rodent that weighed over a ton, roughly the size of a buffalo. The fact that gigantism evolved repeatedly in mammals suggests that large size provides consistent evolutionary advantages when environmental conditions permit. But these giants were always walking a tightrope. Large body size requires specific environmental conditions, abundant food, stable climate, and sufficient habitat. When those conditions changed, giants were often the first to suffer. Their slow reproduction rates, high food requirements, and specialized adaptations made them vulnerable to environmental disruption. The fossil record is littered with giant mammal lineages that flourished for millions of years and then vanished when their world transformed. Paraceratherium disappeared as Asian climates became more arid and seasonal. The Brontotheres died out when their forest habitats shrank. The South American giants faced a double catastrophe when the Isthmus of Panama formed, allowing North American mammals to invade and compete. Yet for tens of millions of years, these giants walked the earth, reshaping ecosystems through their mere presence. They created paths through forests that became highways for smaller animals. They fertilized soil with their waste, spreading seeds and nutrients across vast distances. They modified vegetation through their feeding, creating complex mosaics of habitat types. In a very real sense, the mammals of the Cenozoic reshaped the planet just as profoundly as the dinosaurs had before them. They proved that gigantism wasn't a unique dinosaurian trait, but rather a recurring, evolutionary solution to the challenges and opportunities of terrestrial life. The age of giants never truly ended. It simply changed management. Close your eyes and imagine Antarctica. You're probably picturing endless ice sheets, howling winds, temperatures that plunge to minus 80 degrees Celsius, and a landscape so hostile that nothing can survive there except a few hardy penguins and seals clinging to the coasts. This is Antarctica as we know it today. Earth's frozen fortress, the coldest, driest, windiest continent on the planet. But here's the truth that will completely shatter that image. For most of the Cenozoic era, Antarctica was the exact opposite. It was warm, green, and teeming with life. Forests covered its interior. Rivers flowed through valleys. Mammals wandered beneath canopies of southern beech and ancient conifers. Antarctica wasn't a wasteland. It was paradise. This isn't speculation or fantasy. It's documented fact, written in rocks, fossils, and ice cores that tell a story so extraordinary it seems almost impossible. During the Eocene epoch, from roughly 56 to 34 million years ago, Antarctica enjoyed a temperate climate comparable to modern-day Pacific Northwest forests. Summer temperatures reached 15 to 20 degrees Celsius, comfortable weather for a light jacket. Winter temperatures rarely dropped below freezing. Rainfall was abundant, feeding rivers that carved through landscapes of rolling hills and coastal plains. The continent sat at its current position over the South Pole, but the pole itself wasn't frozen. There was no ice cap, no glaciers, just land covered in vegetation from coast to interior. The evidence for this warm Antarctica comes from multiple sources. Fossilized pollen and spores extracted from deep-sea sediment cores near Antarctica show a diverse assemblage of plants that could only have grown in temperate conditions. Species of Nothofagus, southern beech trees that today grow in New Zealand, Australia, and southern South America, dominated the forests. These trees are adapted to cool but not freezing conditions, with year-round moisture and relatively mild winters. Their presence in Antarctic rocks tells us definitively that the continent experienced climates radically different from today. Even more striking are the fossil leaves themselves. Paleobotanists have recovered beautifully preserved leaf impressions from sites on the Antarctic Peninsula and surrounding islands. These leaves show characteristics typical of temperate forests: broad surfaces for capturing sunlight, smooth edges, drip tips for shedding water. Some of these plants were evergreen, maintaining their leaves year-round. Others were deciduous, dropping their leaves during the long polar winter, when darkness prevailed for months. This deciduous strategy is fascinating because it reveals one of the unique challenges of polar forests: not cold, but darkness. Even in a warm Antarctica, the sun disappeared for several months each winter, forcing plants to develop strategies for surviving without photosynthesis for extended periods. The forests themselves would have been unlike anything existing today. Imagine walking through an Antarctic woodland during the Eocene. The dominant trees are southern beeches, their trunks reaching 60 to 80 feet tall, creating a canopy that filters the constant polar summer sunlight. Mixed among the beeches are conifers, ancestors of modern podocarps and monkey puzzle trees, adding diversity to the canopy structure. The understory is thick with ferns, some reaching tree-like proportions. Mosses carpet the forest floor, thriving in the moist, cool conditions. The air is filled with the calls of birds, the buzzing of insects, and perhaps the sounds of mammals moving through the undergrowth. What mammals lived in this Antarctic paradise? The fossil record here is frustratingly incomplete. Antarctica's subsequent glaciation has buried much of its terrestrial fossil record under miles of ice, making paleontological exploration extraordinarily difficult. But we know from isolated fossil discoveries that marsupials inhabited the continent during the Eocene. These weren't just small, shrew-like creatures. Some were substantial animals, possibly as large as dogs, occupying ecological niches similar to those of placental mammals on other continents. Antarctica was part of a larger southern supercontinent called Gondwana, which had broken apart millions of years earlier, but still maintained biological connections through island-hopping dispersal routes. The presence of marsupials in Eocene Antarctica is particularly significant because it helps explain one of biogeography's great puzzles. Cenozoic marsupials got from South America to Australia. These two continents are now separated by thousands of miles of ocean, yet they share marsupial lineages that must have had a common origin. Antarctica was the bridge. During the Paleocene and early Eocene, when all three southern continents were warmer and still relatively close together, marsupials could migrate between them, using Antarctica as a stepping stone. As the continents drifted apart and Antarctica cooled, this biological highway closed forever, isolating Australian marsupials and allowing them to evolve into the unique forms we see today. Birds were certainly abundant in Antarctic forests. Fossil evidence from nearby islands shows that penguin ancestors were already present during the Eocene, though these early penguins were quite different from modern species. Some were giants, standing 5 feet tall and weighing up to 200 pounds. Others were smaller and probably less specialized for aquatic life than their modern descendants. The fact that penguins evolved in a warm Antarctica is remarkable. It means their aquatic adaptations developed long before the continent froze, driven by the rich marine resources of the Southern Ocean rather than by cold conditions. The coastal waters surrounding Antarctica were remarkably productive during the Eocene. The Southern Ocean teemed with life: fish, squid, marine mammals, and countless invertebrates. The ocean wasn't separated from other water masses by the Antarctic circumpolar current that exists today. Instead, warmer waters from lower latitudes could reach Antarctic shores, bringing heat and nutrients. This made the Antarctic coastline an ideal environment for marine life, supporting complex food webs that extended from microscopic plankton to large predatory sharks and early whales. But the climate that made Antarctica habitable couldn't last forever. Starting around 50 million years ago, subtle changes began to transform the continent's environment. Global temperatures, which had peaked during the early Eocene, started a slow decline. The reasons for this cooling are complex and involve multiple factors acting in concert. Atmospheric CO2 levels were dropping as weathering of rocks and burial of organic material removed carbon from the atmosphere faster than volcanic activity could replace it. Ocean currents were shifting as continents drifted into new positions. And crucially, Antarctica itself was moving into an increasingly isolated position. The most important change was tectonic. Antarctica had once been connected to South America via the Antarctic Peninsula and to Australia via a now submerged landmass. These connections allowed warm ocean currents from the tropics to reach Antarctic waters, helping to maintain the continent's temperate climate. But around 41 million years ago, Australia began its final separation from Antarctica, drifting northward and opening the Tasmanian Gateway. Several million years later, the Drake Passage between Antarctica and South America began to open. These geological events may seem minor, but their climatic consequences were profound. The opening of these gateways allowed the development of the Antarctic Circumpolar Current, a powerful ocean current that flows clockwise around Antarctica, completely encircling the continent. This current, which exists today as the world's largest ocean current, acts as a thermal barrier. It prevents warm waters from lower latitudes from reaching Antarctica, and it traps cold water around the continent. Once the circumpolar current was established, Antarctica's fate was sealed. The continent was thermally isolated, cut off from the heat that had sustained its temperate climate for tens of millions of years. The descent into icehouse conditions wasn't immediate. It took several million years for Antarctica to fully glaciate. During the late Eocene and early Oligocene, around 34 million years ago, the forests began to die back. Summer temperatures declined. Winter freezing became more common. Snow that fell during winter started to persist through summer, accumulating year after year. In mountainous areas, this snow compacted into ice, forming the first glaciers Antarctica had seen in over 100 million years. These glaciers grew, merged, and spread outward from the highlands toward the coasts. The transition from forested continent to ice sheet was catastrophic for Antarctic ecosystems. Species adapted to temperate conditions couldn't survive the cooling. Trees died as growing seasons shortened and temperatures dropped below their tolerance limits. Mammals and birds faced dwindling habitat and food supplies. Some species migrated to warmer areas. This was the last opportunity for animals to leave Antarctica before it became completely isolated by ocean barriers and ice. Those that couldn't migrate faced extinction. By about 25 million years ago, during the Oligocene, Antarctica had transformed into a polar desert, its interior covered by an ice sheet that would grow to encompass the entire continent. The ice itself tells us this story. Scientists have drilled cores deep into the Antarctic ice sheet, extracting ice that is millions of years old. Within this ice are trapped air bubbles, samples of ancient atmosphere that reveal the composition of the air when the ice formed. Dust particles, pollen grains, and chemical signatures in the ice provide additional information about climate conditions. The oldest ice recovered so far is about 800,000 years old, but the rock record beneath the ice extends much further back, preserving evidence of the continent's transformation. Today, Antarctica is buried under ice averaging 1.2 miles thick. In some places, the ice reaches 2.8 miles deep. This represents an almost incomprehensible amount of frozen water, enough to raise global sea levels by 200 feet if it all melted. The weight of the ice has pushed much of the continental bedrock below sea level. The landscape that once supported forests is now crushed beneath billions of tons of ice, its features obscured and altered beyond recognition. Yet the story of Antarctica's lost paradise isn't just a historical curiosity, it's a warning and a preview. It demonstrates that Earth's climate can undergo dramatic shifts over geological timescales, transforming continents from habitable to hostile. The Earth you would have experienced 50 million years ago was a fundamentally different planet from the one we inhabit today. There was no ice at either pole. Palm trees grew in Alaska. Crocodiles basked on Arctic shores. Global average temperatures were 12 to 14 degrees Celsius, warmer than present day. The atmosphere held 3 to 4 times more carbon dioxide than pre-industrial levels, creating a powerful greenhouse effect that distributed heat from equator to poles. This was hothouse Earth, the Eocene climate optimum, and it represented perhaps the warmest sustained period in the past 100 million years. But nothing lasts forever, and what followed was one of the most dramatic climate transformations in Earth's history, a descent from greenhouse warmth to icehouse cold that would reshape continents, redefine oceans, and drive evolution in directions that eventually led to us. The Great Cooling wasn't a sudden event, like the asteroid impact that ended the Cretaceous. It was a gradual transition spanning roughly 20 million years, from about 50 million years ago to 30 million years ago, though its effects continued to intensify for millions of years afterward. Understanding why Earth cooled requires looking at multiple factors operating simultaneously: changes in atmospheric chemistry, shifts in ocean circulation, movements of continents, and feedback loops that amplified initial cooling triggers. It's a story of planetary scale forces interacting in ways we're still working to fully understand. The first, and perhaps most important factor, was the decline in atmospheric carbon dioxide. CO2 is Earth's primary long-term thermostat, controlling global temperatures over millions of years. During the Eocene, volcanic outgassing from mid-ocean ridges and hotspots had maintained high CO2 levels, but by the Middle Eocene, the rate of volcanic CO2 release began to decline. At the same time, several processes were removing CO2 from the atmosphere faster than it was being replenished. Chemical weathering of rocks, particularly silicate minerals, consumes CO2 as rainwater dissolved rocks and carried the carbon to the oceans where it precipitated as limestone. This process accelerates in warm, wet conditions, precisely the conditions that prevailed during the Eocene. The hothouse climate was, in effect, creating conditions that would eventually destroy itself. Mountain building also played a crucial role. Around 50 million years ago, India, which had been racing northward across the Tethys Ocean, finally collided with Asia. This wasn't a gentle merger. India plowed into the Asian continent with such force that it crumpled the crust, pushing up the Himalayas and the Tibetan Plateau, the largest and highest landmass on Earth. This uplift exposed vast quantities of fresh rock to weathering. The monsoons that developed as a result of the plateau's elevation brought intense rainfall, accelerating chemical weathering and pulling even more CO2 from the atmosphere. Some scientists estimate that the rise of the Himalayas and Tibetan Plateau could have reduced atmospheric CO2 by 30 to 40% over the course of the Cenozoic. But CO2 decline alone doesn't fully explain the cooling. Ocean circulation changes were equally important, and here we return to Antarctica. As discussed earlier, the opening of the Drake Passage and Tasmanian Gateway between 41 and 34 million years ago allowed the formation of the Antarctic Circumpolar Current. This current thermally isolated Antarctica, preventing warm tropical waters from reaching the continent. But its effects extended far beyond Antarctica itself. The circumpolar current changed the entire pattern of global ocean circulation, affecting heat distribution around the planet. It strengthened the temperature gradient between equator and poles, making polar regions colder while tropical regions remained warm. This increased gradient intensified atmospheric circulation, creating the stronger, more organized wind patterns and ocean currents that characterize the modern climate system. The cooling's effects on Antarctica were immediate and dramatic. Around 34 million years ago, at the boundary between the Eocene and Oligocene epochs, Antarctic temperatures dropped below a critical threshold. Summer snow began to persist year-round in highland areas. Ice accumulated, forming glaciers that grew and merged into ice sheets. This transition happened remarkably quickly in geological terms. Within perhaps 400,000 years, Antarctica transformed from a forested continent to an ice-covered landmass. The ice sheets reflected sunlight back to space, a phenomenon called the ice albedo feedback, which further cooled the continent and allowed the ice to expand. Once this process began, it became self-reinforcing. More ice meant more reflection, which meant more cooling, which meant more ice. The formation of Antarctic ice sheets had global consequences. Sea levels dropped by approximately 70 meters as water was locked up in ice, exposing continental shelves and changing coastlines worldwide. Ocean chemistry shifted as the formation of deep cold water around Antarctica drove changes in thermohaline circulation, the global conveyor belt of ocean currents that distributes heat and nutrients. The production of Antarctic bottom water, the coldest and densest water in the world's oceans, began during this period and continues today, supplying the deep ocean with oxygen-rich water and driving deep-sea circulation. Life responded to the cooling in dramatic ways. In the oceans, many species adapted to warm conditions went extinct, particularly in high latitudes. Coral reefs retreated toward the tropics. Warm water plankton species disappeared from polar regions, replaced by cold-adapted forms. On land, the effects were equally profound. The tropical and subtropical forests that had stretched to high latitudes began to retreat toward the equator. In their place came temperate forests, dominated by deciduous trees, species that could tolerate seasonal cold by shedding their leaves and going dormant during winter. At even higher latitudes, forests gave way to tundra and eventually ice. Mammalian evolution was profoundly shaped by this cooling trend. The warm adapted species of the Eocene found their habitats shrinking. Many went extinct, unable to adapt to the changing conditions. But others evolved remarkable adaptations for dealing with cooler, more seasonal climates. One of the most important adaptations was the development of hypsodonty, high-crowned teeth with thick enamel, suitable for processing tough, abrasive vegetation. This trait would become crucial in the next phase of mammalian evolution as grasslands expanded, but its origins lie in the Oligocene as mammals adapted to eating coarser vegetation in cooling climates. Body size also shifted in response to climate change. In many lineages, animals got larger during the Oligocene and Miocene. This follows a pattern called Bergmann's rule, which states that within a species or closely related groups, individuals in colder climates tend to be larger than those in warmer climates. The reasoning is thermodynamic. Larger bodies have a lower surface area to volume ratio, which helps retain heat. This wasn't universal. Some lineages evolved smaller sizes for other reasons, but the trend toward gigantism in many mammal groups during the cooling period is striking. The Arctic followed a different trajectory than Antarctica, but it too felt the effects of global cooling. The Arctic Ocean is surrounded by continents rather than being isolated like Antarctica, which prevented the formation of a similar circumpolar current. However, as global temperatures declined, the Arctic progressively cooled. Forests retreated southward, replaced first by tundra, and eventually, though not until much later in the Cenozoic, by sea ice. The formation of Arctic ice was delayed compared to Antarctica, not beginning in earnest until the Pliocene epoch around 3 million years ago. This timing difference reflects the different geography. Antarctica's isolation allowed it to cool faster, while the Arctic's connection to warm ocean currents from lower latitudes delayed ice formation. By the Miocene epoch, from 23 to 5 million years ago, Earth had settled into a new climate regime. It was cooler than the Eocene, but warmer than today, a middle ground between hothouse and icehouse. Temperatures fluctuated, with some periods of warming and others of enhanced cooling, but the overall trend was downward. Antarctica remained frozen, its ice sheets waxing and waning with climate variations, but never disappearing entirely. The Arctic was cool, but not yet ice-covered. Mid-latitudes experienced temperate climates with distinct seasons, warm summers and cool winters, a pattern familiar to those of us living in such regions today. This Miocene world was characterized by increasing climatic variability. The stable, warm conditions of the Eocene were gone, replaced by a more dynamic climate system, with stronger seasonal contrasts and more pronounced differences between tropical and polar regions. This variability drove evolutionary innovation. Species that could adapt to changing conditions thrived. Those that couldn't went extinct. The fossil record shows increasing rates of turnover, species appearing and disappearing more rapidly than in the stable Eocene climate. Evolution was accelerating, driven by environmental instability. One particularly important development during the Miocene was the expansion of C4 photosynthesis in grasses. This is a biochemical pathway that allows plants to photosynthesize more efficiently in hot, dry conditions and at low CO2 concentrations. As atmospheric CO2 continued to decline through the Miocene, reaching levels approaching modern values, C4 grasses gained a competitive advantage over C3 plants, which use a more primitive photosynthetic pathway. This biochemical innovation would enable the grassland expansion that transformed ecosystems in the late Miocene and Pliocene. The Great Cooling also affected ocean productivity in complex ways. Cold water holds more dissolved oxygen than warm water, and it can dissolve more nutrients. The formation of cold, deep water around Antarctica enriched the deep ocean with oxygen and nutrients. When this water upwelled in certain regions, along western continental margins, near Antarctica, and in equatorial zones, it brought nutrients to the surface, fueling explosions of plankton growth. These productive upwelling zones became hotspots of marine life, supporting fish, marine mammals, and seabirds in remarkable abundance. Some of the world's richest fisheries today are located in regions where cold, nutrient-rich water rises from the depths. By about 15 million years ago, in the Middle Miocene, global climate had cooled to the point where ice sheets periodically formed in the northern hemisphere as well, though these were smaller and less permanent than Antarctica's ice. Mountain glaciers appeared in high elevation areas. Sea ice occasionally formed in the Arctic Ocean during winter. The stage was being set for the ice ages that would dominate the Pleistocene epoch, though those dramatic glaciations were still millions of years in the future. The Great Cooling transformed Earth from a uniform, warm greenhouse into a planet of climatic extremes and contrasts. For most of the Cenozoic Era, forests dominated the continents. From the tropical jungles of the Eocene to the temperate woodlands of the Oligocene and early Miocene, trees were the default vegetation across most of Earth's land surface. Grasslands existed, but they were marginal habitats, small patches in areas too dry, too cold, or too frequently disturbed for trees to thrive. Grasses themselves were relatively uncommon plants, overshadowed by more successful vegetation types. But starting around 20 million years ago, something extraordinary began to happen. Grasslands started to expand, spreading across continents in a wave of ecological transformation that would reshape the planet more profoundly than almost any other event in the Cenozoic. This wasn't just a change in plant communities. It was a revolution that restructured food webs, drove evolutionary innovation, altered global climate, and ultimately created the landscapes where human civilization would emerge. To understand the grasslands revolution, you first need to understand what makes grasses special. Grasses are not typical plants. They evolved a unique architecture that allows them to survive conditions that would kill most other vegetation. Unlike trees or shrubs, which grow from their tips, grasses grow from their base near ground level. This means that when the top of a grass plant is eaten, trampled, or burned, the plant doesn't die. It simply grows back. This growth strategy makes grasses extraordinarily resilient to disturbance, particularly grazing and fire, two forces that would increase dramatically as grasslands expanded. Grasses also developed another crucial adaptation: the ability to photosynthesize efficiently in hot, dry conditions and at low carbon dioxide concentrations. This adaptation, called C4 photosynthesis, evolved independently in multiple grass lineages during the Oligocene and Miocene epochs. Traditional C3 photosynthesis, which most plants use, becomes inefficient when temperatures rise and CO2 levels fall, because the enzymes involved in the process start capturing oxygen instead of carbon dioxide, wasting energy. C4 plants evolved a biochemical workaround that concentrates CO2 at the site of carbon fixation, making photosynthesis much more efficient under stress conditions. As global CO2 levels continued their long-term decline from Eocene highs, reaching values similar to pre-industrial levels by the late Miocene, C4 grasses gained a decisive competitive advantage. But having efficient physiology isn't enough to explain why grasslands expanded so dramatically. Climate change was the primary driver. As Earth cooled through the Oligocene and Miocene, precipitation patterns shifted. Many continental interiors became drier as the temperature gradient between equator and poles strengthened, altering atmospheric circulation. The great forests that had covered these regions began to fragment. Trees require reliable rainfall to survive. Most tree species need at least 500 millimeters of rain per year, distributed relatively evenly across seasons. When rainfall became more seasonal, or declined below this threshold, trees struggled. Grasslands, which can survive and even thrive in areas receiving as little as 250 millimeters of rain per year, moved in to fill the gaps. The expansion wasn't instantaneous. It happened in pulses, spread over millions of years, with grasslands advancing during dry periods and retreating during wetter intervals. But the overall trend was clear. By about 8 million years ago, during the late Miocene, extensive grasslands covered large portions of every continent except Antarctica. The Great Plains of North America, the pampas of South America, the steppes of Central Asia, the savannas of Africa. These iconic landscapes all emerged during this period. Where once there had been continuous forests, now there were vast open spaces where grass stretched to the horizon, punctuated by scattered trees, or gallery forests along rivers. The ecological consequences of grassland expansion were profound and immediate. Grasslands represent a fundamentally different type of ecosystem from forests. They're more productive in terms of leaf biomass per year. Grass grows fast, dies back, and regrows in endless cycles. But that productivity is concentrated near ground level, rather than being distributed vertically through a canopy. This creates different opportunities and challenges for animals. In forests, resources are distributed three-dimensionally, with different species occupying different vertical zones. In grasslands, most resources are at ground level, creating intense competition in a two-dimensional space. Herbivorous mammals responded to grassland expansion with a burst of evolutionary innovation. The most important adaptation was the development of high-crowned, continuously growing teeth, called hypsodont teeth. Grass is incredibly abrasive. It incorporates silica into its tissues as a defense against herbivores, and grasslands accumulate dust and grit that stick to the vegetation. Eating grass is like chewing sandpaper, and it wears down teeth rapidly. The low-crowned teeth that had served mammals well in forest environments, where they ate soft leaves and fruits, were inadequate for a grass-based diet. Hypsodont teeth, with their tall crowns and thick enamel, could withstand decades of wear. And in some species, they continued growing throughout the animal's life, never wearing out completely. Horses provide the classic example of adaptation to grasslands. During the Eocene, horses were small, forest-dwelling browsers with low-crowned teeth and multiple toes on each foot, well suited for navigating soft forest floors. As grasslands expanded through the Miocene, horse evolution accelerated. They grew larger, increasing from dog-sized to pony-sized to the full-sized horses we know today. Their teeth became progressively taller and more complex, capable of processing tough grasses. Their legs lengthened and their toes reduced from multiple digits to a single hoof, creating a limb structure optimized for efficient running on hard, open ground. By the late Miocene, horses had transformed from forest browsers into grassland specialists, and they diversified into numerous species that filled ecosystems across North America and Eurasia. But horses were just one success story. The grasslands revolution drove adaptive radiations in numerous mammalian lineages. Bovids, the group that includes cattle, antelopes, sheep, and goats, diversified explosively during the Miocene, evolving from a handful of species into dozens of specialized forms. Some became massive grazers like buffalo. Others became fast runners like gazelles, using speed to escape predators in open environments where hiding was impossible. Still, others became specialized for different vegetation types or microhabitats within grasslands. Each species represented a slightly different solution to the challenges of grassland life. In South America, which had been isolated from other continents for most of the Cenozoic, grasslands triggered similar evolutionary responses in completely different mammalian lineages. Notungulates and litopterns, bizarre groups of native South American herbivores, evolved high-crowned teeth and cursorial legs, converging on body plans similar to horses and antelopes, despite being only distantly related. This is evolution's most powerful demonstration. Given similar environmental challenges, unrelated lineages independently evolve similar solutions, a phenomenon called convergent evolution. Predators adapted to grasslands as well. In forests, ambush hunting is effective. Predators can hide in dense vegetation and surprise prey. But in open grasslands, hiding is difficult. This favored the evolution of cursorial predators, fast runners that could chase down prey over long distances. The dog family, Canidae, diversified during the Miocene as grasslands expanded, evolving longer legs, more efficient cardiovascular systems, and pack hunting behaviors that allowed them to bring down large prey. Cats followed a different strategy, becoming powerful sprinters capable of brief bursts of extraordinary speed, ambushing prey from the limited cover available in grassland environments. Perhaps most significantly, grasslands drove the evolution of intelligence and social behavior. Open environments are dangerous. There's nowhere to hide from predators, and resources are often patchily distributed. These conditions favor social living, where multiple individuals cooperate to watch for danger, defend against predators, and locate food. Many grassland mammals evolved complex social structures. Horses formed herds with sophisticated hierarchies. Bovids developed various social systems, from solitary to large migratory herds numbering in the thousands. Primates adapted to grassland edges and savanna environments, and it was in these habitats that the ancestors of humans would eventually evolve enhanced intelligence, bipedalism, and tool use, adaptations that made sense in open, resource-variable environments. The grasslands revolution also transformed global biogeochemistry. Grasslands and forests process carbon differently. Forests store most of their carbon in wood, trunks, branches, and roots that persist for decades or centuries. Grasslands store less carbon above ground because grass dies back seasonally, but they can store enormous amounts of carbon in soil as organic matter and root systems. As grasslands expanded, the global distribution of carbon storage shifted. Additionally, the expansion of C4 grasses changed the isotopic signature of carbon in the environment, a change so pronounced that scientists can track it in fossil teeth, soil carbonates, and ocean sediments. This C4 expansion is one of the most distinctive biogeochemical signatures in the geological record of the past 10 million years. Fire regimes also changed dramatically. Grasslands and fire have a symbiotic relationship. Grass provides abundant, fine fuel that burns easily, and grasslands naturally burn frequently. But fire doesn't kill grass. Remember, grasses grow from ground level and can regrow quickly after burning. Fire actually benefits grasslands by removing dead material, recycling nutrients, and killing tree seedlings that might otherwise invade. As grasslands expanded, fire frequency increased across continents. Evidence from charcoal deposits in ancient soils shows a spike in fire activity during the late Miocene, coinciding precisely with grassland expansion. These fires had continental-scale impacts, affecting vegetation patterns, carbon cycling, and atmospheric chemistry. The grasslands revolution even influenced climate, creating feedback loops that reinforced the conditions that favored grasslands in the first place. Grasslands have higher albedo than forests. They reflect more sunlight, which tends to cool local and regional climates. They also recycle water differently, sending less moisture back to the atmosphere through transpiration than forests do, which can reduce rainfall in downwind areas. These effects likely reinforced the drying trend that had initiated grassland expansion, creating a self-sustaining cycle. By the Pliocene epoch, 5 million years ago, grasslands had become one of Earth's dominant biomes, rivaling forests in extent and ecological importance. The planet had been fundamentally restructured. Where once there had been relatively uniform forest coverage with variations in species composition, now there was a complex mosaic of biomes: tropical rainforests, temperate forests, boreal forests, grasslands, savannas, steppes, deserts, and tundra. 2.5 million years ago, Earth's climate crossed a threshold from which there would be no return. The long cooling trend that had begun 50 million years earlier reached a tipping point, and the planet plunged into the Pleistocene epoch, the Ice Age. But here's what most people misunderstand about the Ice Age. It wasn't a single period of continuous cold. It was a roller coaster of climate extremes, a series of devastating glacial periods separated by warmer, interglacial intervals, with temperatures swinging wildly between the two states on timescales of tens of thousands of years. During glacial maxima, ice sheets up to 2 miles thick covered Canada, northern Europe, and parts of Asia. Sea levels dropped by 400 feet as water was locked in ice. Entire ecosystems shifted southward, and megafauna, giant mammals unlike anything alive today, roamed landscapes of tundra, steppe, and cold grassland. This was the world that forged modern humanity, a planet of extremes that tested life's resilience like never before. The transition into the Pleistocene wasn't sudden. It was the culmination of processes that had been building for millions of years. By 3 million years ago, permanent ice sheets had formed in the northern hemisphere, centered on Greenland and the mountains of Alaska and northern Canada. But these ice sheets were relatively small and stable. Around 2.6 million years ago, something changed. The ice sheets began to expand and contract rhythmically, advancing across continents during cold periods and retreating during warm intervals. Scientists call these oscillations glacial interglacial cycles, and they became the defining characteristic of Pleistocene climate. Over the past 2.6 million years, Earth has experienced at least 50 of these cycles, each one transforming the planet's surface and driving evolutionary change. What caused these cycles? The answer lies in subtle variations in Earth's orbit and rotation, collectively known as Milankovitch cycles, after the Serbian mathematician who first described them. Earth's orbit around the Sun isn't perfectly circular. It varies from more circular to more elliptical over a cycle of about 100,000 years. The tilt of Earth's axis, which causes our seasons, varies between 22.1 and 24.5 degrees over a 41,000-year cycle. And the axis itself wobbles like a spinning top, completing a full precession cycle every 26,000 years. None of these orbital variations changes the total amount of sunlight Earth receives by much, but they dramatically affect how that sunlight is distributed across seasons and latitudes. When orbital configurations reduce summer sunlight in northern latitudes, snow that falls during winter doesn't completely melt during summer. Year after year, it accumulates, compacts into ice, and eventually forms continental ice sheets. The ice sheets themselves were staggering in scale. During the last glacial maximum, about 20,000 years ago, the Laurentide ice sheet covered all of Canada and extended into the northern United States, reaching as far south as New York, Ohio, and Montana. In places, it was over 10,000 feet thick, twice the height of the tallest skyscrapers. The Scandinavian ice sheet covered northern Europe from the British Isles to western Russia. Smaller ice sheets covered the Andes, the Himalayas, and mountain ranges worldwide. Even regions that weren't directly covered by ice were transformed. The weight of the ice sheets was so enormous that it pressed down the Earth's crust, depressing it by hundreds of meters, a deformation that's still rebounding today in places like Scandinavia and Canada. With so much water locked in ice, sea levels plummeted. Continental shelves, the shallow underwater margins of continents, were exposed as dry land. The English Channel didn't exist during glacial maxima. Britain was connected to Europe by a land bridge called Doggerland, a region now submerged but once inhabited by humans and megafauna. The Bering Land Bridge connected Alaska to Siberia, allowing animals and eventually humans to migrate between Asia and North America. Indonesia, Malaysia, and the Philippines were connected in a landmass called Sundaland. These land bridges were crucial highways for the dispersal of species, allowing populations to spread into new territories that are now separated by ocean barriers. The climate of glacial periods was harsh beyond modern experience. Global average temperatures were 4 to 7 degrees Celsius colder than today, a difference that sounds modest but had devastating effects. The regions immediately south of the ice sheets experienced perpetual winter conditions, with frigid winds blowing off the ice, creating vast periglacial zones of tundra and cold steppe. Rainfall patterns shifted dramatically. Many tropical regions became drier because cooler oceans produced less evaporation, reducing the moisture available for precipitation. The Amazon rainforest shrank to isolated refugia surrounded by grassland and savanna. The Sahara Desert expanded. Vegetation zones worldwide shifted toward the equator, compressed into narrower bands as ice claimed the high latitudes. Into these harsh environments came the megafauna, Pleistocene giants that adapted to life in a frozen world. These weren't dinosaurs or ancient evolutionary lineages. They were mammals, close relatives of species alive today, but grown to enormous sizes and equipped with spectacular adaptations for cold climates. The most iconic was the woolly mammoth, a species of elephant adapted to tundra environments. Standing 11 feet tall at the shoulder and weighing up to 6 tons, mammoths were covered in thick, shaggy hair, up to 3 feet long, with a dense undercoat for insulation. They had small ears and short tails compared to tropical elephants, reducing surface area and minimizing heat loss. Their curved tusks, which could reach 15 feet in length, were used to sweep snow aside to reach the grasses and sedges they fed on. Mammoths weren't confined to one region. They ranged across the entire northern hemisphere, from Spain to Siberia to North America, dominating the mammoth steppe ecosystem that stretched across these continents. The woolly rhinoceros was equally impressive, standing 6 feet tall and weighing up to 2 tons, with 2 horns, the front one reaching up to 3 feet long. Like mammoths, they were covered in thick fur and adapted to feeding on the tough, cold-resistant vegetation of glacial environments. Cave bears, much larger than modern bears, hibernated in caves across Europe, leaving claw marks and bones that have been found by the thousands. The giant short-faced bear of North America stood 12 feet tall on its hind legs and may have weighed 1,500 pounds, making it one of the largest carnivorous mammals ever to exist. But perhaps the most fascinating megafauna were the giant ground sloths of the Americas. These weren't the small, slow-moving tree sloths we know today. Megatherium, the largest species, stood 20 feet tall on its hind legs and weighed up to 4 tons, as much as a modern elephant. They had massive claws, powerful limbs, and the ability to rear up and strip branches from trees. Despite their size, they were herbivores, using their bulk primarily for defense and reaching high vegetation. They ranged from Patagonia to Alaska, adapting to environments from tropical forests to cold grasslands. In Australia, a continent isolated from other land masses, evolution produced its own unique megafauna. Diprotodon, a marsupial the size of a rhinoceros, was the largest marsupial ever to exist. It weighed up to 3 tons and browsed on vegetation across Australia's interior. The marsupial lion, Thylacoleo, was a carnivorous marsupial with the most powerful bite force relative to body size of any mammal. It hunted Diprotodon and other large herbivores using massive blade-like premolars that functioned like shears. Giant kangaroos stood 10 feet tall. Enormous wombats weighing 600 pounds dug burrow systems that still exist today. This was a parallel universe of mammalian evolution, producing solutions to the same ecological challenges using completely different evolutionary starting materials. The Pleistocene was also the age of the saber-toothed cats. Multiple lineages independently evolved elongated canine teeth designed for delivering devastating bites to large prey. Smilodon, the most famous, roamed the Americas with canines that extended 7 inches beyond the gums. These weren't stabbing weapons. The teeth were too fragile for that. Instead, saber-tooths used their powerful neck muscles to deliver precise slashing bites to vulnerable areas of prey, causing massive blood loss. They hunted the mega herbivores that dominated Pleistocene ecosystems, animals so large that modern predators would struggle to bring them down. The glacial-interglacial cycles created a dynamic, unstable environment that drove rapid evolutionary change. Species adapted to cold conditions thrived during glacial maxima, but faced extinction during warm interglacials. Species adapted to warmth survived interglacials, but had to retreat to refugia during glacial advances. The constant climate oscillations acted as a pump, forcing species to adapt, migrate, or die. This environmental instability selected for flexibility, intelligence, and behavioral plasticity, traits that would prove crucial for one particular primate lineage. The Pleistocene also witnessed the emergence and spread of the genus Homo. Our ancestors evolved in Africa during the Pliocene and early Pleistocene, but it was during the glacial cycles that various human species dispersed across the Old World. Homo erectus reached Southeast Asia and China. Homo heidelbergensis spread across Europe and Africa. Neanderthals evolved in Europe, becoming perfectly adapted to glacial conditions with stocky bodies, large nasal cavities for warming cold air, and sophisticated tool technologies. Denisovans, a recently discovered human lineage known primarily from DNA, inhabited Asia. And Homo sapiens, our own species, emerged in Africa around 300,000 years ago, eventually spreading across the entire planet. These human species weren't passive observers of the Pleistocene world. They were active participants, hunting megafauna, using fire to modify landscapes, and developing technologies that allowed them to survive in almost any environment. There's ongoing debate about the role humans played in megafaunal extinctions, but it's clear that human hunting pressure, combined with rapid climate change at the end of the last glacial period, was devastating for large mammals. Starting about 50,000 years ago and accelerating after 15,000 years ago, megafauna began to disappear. Mammoths, mastodons, giant ground sloths, woolly rhinos, cave bears, saber-toothed cats, all vanished in a geological instant, leaving behind only fossils and the species we have today. Of all the evolutionary achievements of the Cenozoic Era, perhaps none is more remarkable than the rise of mammals to complete planetary dominance. In just 66 million years, a brief moment in geological time, mammals transformed from small, nocturnal creatures cowering in the shadows of dinosaurs into the most successful group of large animals on Earth. They conquered every habitat imaginable: deep oceans, high mountains, scorching deserts, frozen tundra, dense forests, and open grasslands. They learned to fly, to swim, to burrow, to climb, and to run faster than any other vertebrates. They evolved intelligence, complex social behaviors, and technologies that would eventually reshape the planet itself. The mammalian conquest of Earth represents one of evolution's greatest success stories, and it was driven by one key advantage: their extraordinary capacity for adaptation. Understanding mammalian success requires understanding what makes mammals different from other vertebrates. At first glance, mammals might not seem particularly special. They're warm-blooded, but so are birds. They have hair, but many reptiles have scales that serve similar functions. They give birth to live young, but so do many fish and reptiles. It's not any single trait that makes mammals exceptional. It's the combination of characteristics that creates a uniquely flexible and adaptable body plan. Mammals maintain constant body temperatures through internal heat generation, allowing them to remain active in cold conditions when other animals become sluggish. They have efficient cardiovascular and respiratory systems that can support high activity levels. Their brains are large relative to body size and highly developed, enabling complex behaviors and rapid learning. They have differentiated teeth that can be specialized for various diets. And perhaps most importantly, they have extended parental care that allows complex behaviors and knowledge to be passed from generation to generation. These mammalian characteristics didn't evolve overnight. The basic mammalian body plan was established during the Mesozoic era. refined over more than 100 million years of evolution alongside dinosaurs. But it was only after the KPG extinction removed dinosaurian competition that mammals could fully exploit their adaptive potential. What followed was an evolutionary explosion unlike anything seen before or since in vertebrate history. Within 10 million years of the extinction, the early Paleocene, mammals had diversified into dozens of major lineages, each exploring different ecological strategies. This wasn't just filling empty niches, it was creating entirely new ways of living. The first major adaptive breakthrough was size. As we've seen, mammals quickly grew from shrew-sized creatures to animals rivaling the largest dinosaurs. But size alone wasn't enough. True success came from behavioral and physiological adaptations that allowed mammals to thrive in environments where reptiles struggled. Take cold tolerance as an example. Reptiles are largely confined to warm climates because their metabolism depends on external heat sources. When temperatures drop, they become inactive. Mammals, with their internal heat generation and insulating hair or fur, could remain active in cold conditions. This gave them access to high-latitude environments and allowed them to exploit seasonal resources that other animals couldn't use effectively. Mammalian intelligence proved to be another decisive advantage. While reptilian brains are efficient for stereotyped behaviors, mammalian brains are built for flexibility. The expanded cerebral cortex in mammals enables complex information processing, memory formation, and behavioral modification based on experience. This neurological architecture allowed mammals to adapt to changing conditions within their own lifetimes, rather than waiting for evolutionary change across generations. A mammal could learn which foods were safe, remember the locations of resources, modify its behavior based on predator encounters, and even develop new techniques for obtaining food or avoiding danger. Perhaps nowhere is mammalian adaptability more evident than in their dietary flexibility. Early mammals were primarily insectivores, but as they diversified, they explored virtually every possible feeding strategy. Some became specialized herbivores, developing complex digestive systems with multiple stomach chambers and symbiotic bacteria to break down cellulose. Others became carnivores, evolving sharp teeth, powerful jaws, and hunting behaviors. Many became omnivores, capable of switching between plant and animal foods as availability changed. This dietary flexibility was crucial during the climate fluctuations of the Cenozoic, allowing mammalian populations to survive environmental changes that drove more specialized species to extinction. The colonization of aquatic environments represents one of mammals' most spectacular adaptive achievements. Multiple mammalian lineages independently returned to the water, each solving the challenges of aquatic life in different ways. The evolution of whales is perhaps the most dramatic example. Starting from small, wolf-like terrestrial mammals around 50 million years ago, whale ancestors underwent one of the most complete morphological transformations in the fossil record. Over just 15 million years, they evolved from four-legged land animals into fully aquatic creatures with streamlined bodies, paddle-like limbs, and tail flukes. Their nostrils migrated from the front of the skull to the top, becoming blowholes. Their bones became denser to provide ballast underwater. Their limb bones restructured completely to form flippers. Some species developed echolocation systems more sophisticated than any human sonar technology. But whales weren't the only mammals to conquer aquatic environments. Seals and sea lions evolved from bear-like ancestors, developing flippers while retaining the ability to move on land. Manatees and dugongs, the sirenians, evolved from four-legged herbivores into fully aquatic plant eaters. Otters became semi-aquatic specialists, using tools to crack open shellfish. Even some primates, like proboscis monkeys, became adapted to life in aquatic mangrove environments. Each lineage found its own solution to the challenges of aquatic life, demonstrating the flexibility of the basic mammalian body plan. Aerial environments presented different challenges, but mammals conquered those as well. Bats evolved powered flight independently from birds, developing wing membranes stretched between elongated finger bones. This membrane design is actually more maneuverable than bird wings, allowing bats to perform aerial acrobatics that birds cannot match. Bats diversified into over 1,400 species, nearly a quarter of all mammal species, exploiting every aerial niche from tiny insectivores to large fruit eaters to vampires that feed on blood. Some evolved echolocation systems that rival those of whales, capable of detecting wires as thin as human hair in complete darkness. Underground environments also attracted mammalian colonists. Moles evolved powerful forelimbs for digging, reduced eyes for life in perpetual darkness, and sensitive snouts for detecting prey through touch and smell. Ground squirrels, prairie dogs, and other rodents created extensive burrow systems that provide protection from predators and climate extremes. Some mammals, like naked mole rats, evolved eusocial behavior similar to insects, with a single breeding queen supported by non-reproductive workers, a social system unique among mammals. The Arctic represents one of Earth's most challenging environments, yet mammals found ways to thrive there as well. Polar bears evolved from brown bears, developing white fur for camouflage, massive paws for walking on ice, and the ability to swim long distances in frigid water. Arctic foxes grow thick winter coats that change from brown to white with the seasons. Caribou migrate thousands of miles annually, following the brief Arctic growing season. Seals and walruses use sea ice as breeding platforms, while feeding in the rich waters beneath. Each species developed unique solutions to the challenges of extreme cold, seasonal light variation, and limited food availability. Desert environments pose different challenges: extreme heat, water scarcity, and sparse vegetation. Mammals responded with remarkable physiological adaptations. Desert rodents like kangaroo rats can survive without ever drinking water, obtaining all necessary moisture from the seeds they eat and producing extremely concentrated urine to minimize water loss. Camels store fat in their humps rather than under their skin, reducing insulation and helping them stay cool. Fennec foxes have enormous ears that act as heat radiators, dissipating excess body heat. Some desert mammals are nocturnal, avoiding daytime heat by remaining in burrows and becoming active only when temperatures drop. Mountain environments present challenges of low oxygen, extreme cold, and steep terrain. Mammals adapted with enlarged hearts and lungs for extracting oxygen from thin air, sure-footed locomotion for navigating rocky terrain, and thick coats for insulation. Mountain goats and sheep develop specialized hooves with soft pads for gripping rock surfaces. High-altitude rodents, like pikas, gather and dry vegetation during summer, creating hay piles that sustain them through harsh winters. Some mammals, like yaks, became so well adapted to high altitudes that they struggle to survive at sea level. Perhaps the most impressive mammalian adaptation is intelligence itself. While many mammals are intelligent, primates pushed cognitive abilities to extraordinary levels. The evolution of larger brains, enhanced memory, complex social behaviors, and eventually tool use created positive feedback loops that accelerated intellectual development. Primates learned to use sticks to extract insects, stones to crack nuts, and leaves as sponges. They developed complex communication systems, intricate social hierarchies, and cultural traditions passed from generation to generation. In one lineage, our own, intelligence became so advanced that it fundamentally altered the relationship between organisms and their environment. Human intelligence represents the ultimate expression of mammalian adaptability. Rather than evolving specialized physical adaptations for different environments, humans develop technology that allows the same basic body plan to survive anywhere on Earth and even beyond it. Clothing replaces fur for insulation. Tools extend the capabilities of hands and teeth. Fire provides external heat and allows cooking, which pre-digests food and makes nutrients more available. Language enables the accumulation and transmission of knowledge across generations at speeds that dwarf genetic inheritance. Agriculture allows the modification of environments to increase resource production. The mammalian conquest of Earth wasn't just about physical adaptations. It was about the evolution of behavioral flexibility, learning ability, and social cooperation that allowed mammals to modify their behavior faster than environments could change. This adaptability has made mammals the dominant large animals on every continent and in every major habitat. From the smallest shrews to the largest whales, from the most social primates to the most solitary cats, mammals have demonstrated that success in evolution comes not from perfect specialization for a single environment, but from the ability to adapt to whatever challenges the world presents. In the grand sweep of the Cenozoic Era, spanning 66 million years of mammalian evolution, continental drift, and climate transformation, one lineage stands apart. Not because it was the largest, the fastest, or the most numerous, but because it developed something unprecedented in the history of life on Earth: the ability to understand and manipulate the planet itself. That lineage is our own, the genus Homo, and our story represents the most recent chapter in the Cenozoic saga. We are not separate from this deep history. We are its product, forged by the same evolutionary forces that shaped every other organism, but equipped with cognitive abilities that would eventually allow us to transcend purely biological evolution and reshape the world according to our will. The human story begins not with humans, but with primates, a group that first appeared during the Paleocene epoch over 60 million years ago. These earliest primates were small, squirrel-like creatures that lived in the tropical forests, covering much of the planet after the dinosaur extinction. They had grasping hands with opposable digits, an adaptation for life in trees where the ability to grip branches meant the difference between survival and a fatal fall. They had forward-facing eyes that provided binocular vision, allowing accurate depth perception, crucial for judging distances when leaping between branches. These might seem like simple adaptations, but they set primates on an evolutionary trajectory that would eventually lead to enhanced manual dexterity and visual spatial intelligence. For tens of millions of years, primates remained tropical forest dwellers, diversifying into lemurs, lorises, tarsiers, monkeys, and apes. They grew larger, their brains expanded, and their social behaviors became more complex. By the Miocene epoch, Around 20 million years ago, apes had become widespread across Africa and Eurasia. These weren't the giant apes we think of today. They ranged from small, gibbon-sized species to larger forms, and they occupied diverse ecological niches in forests and woodlands. They had larger brains relative to body size than other primates, longer developmental periods, allowing extended learning and increasingly complex social structures. Then, between 10 and 5 million years ago, something crucial happened. Africa's climate was changing as part of the global cooling trend and grassland expansion we discussed earlier. The continuous forests that had covered much of the continent began to fragment, replaced by a mosaic of forest patches, woodland, and open grassland, the savanna environment that characterizes much of Africa today. For forest-adapted apes, this was a crisis. Their habitat was disappearing. Most ape lineages went extinct or retreated to the shrinking forest refugia, but one lineage responded differently. They ventured into the open, adapting to life at the forest edge and eventually in the grasslands themselves. This transition required fundamental changes in locomotion. In forests, apes moved by climbing and swinging through branches. In open environments, efficient terrestrial movement became crucial. Most mammals solved this problem by becoming quadrupedal, moving on all fours. But the ape lineage that would give rise to humans took a different path. They became bipedal, walking upright on two legs. This is one of the defining characteristics of the human lineage, appearing at least 6 to 7 million years ago in species like Sahelanthropus and Orrerin, and fully developed by 4 million years ago in Australopithecus. Why bipedalism? The answer remains debated, but likely involves multiple factors. Walking upright is more energy efficient than quadrupedal knuckle walking when traveling long distances in open environments, crucial when resources are scattered across the landscape. It elevates the head, improving visibility over tall grass and allowing early detection of predators or prey. It reduces the body surface exposed to intense midday sun, helping with heat management. And critically, it frees the hands for carrying objects, food, tools, infants, something that becomes increasingly important as our ancestors' dependence on technology grew. The Australopithecines, who lived between 4 and 2 million years ago, represent this transitional phase. Species like Australopithecus afarensis, famously represented by the skeleton Lucy, were fully bipedal, but retained many ape-like features. They had small brains, about 400 to 500 cubic centimeters, roughly the size of a chimpanzee's. They were small-bodied, standing about 3 to 4 feet tall. Their diet was varied, including fruits, leaves, and possibly some meat. They made simple stone tools, or at least used unmodified stones as tools, a behavior observed in some modern primates as well. These were not yet humans, but they were on the path. The transition from Australopithecines to Homo occurred around 2.5 to 2 million years ago, during a period of increased climate variability in Africa. The Pleistocene glacial cycles were beginning, and Africa experienced oscillations between wetter and drier conditions. This environmental instability may have selected for behavioral flexibility and intelligence, traits that would become hallmarks of the genus Homo. The earliest Homo species, like Homo habilis, showed increased brain size to about 600 to 700 cubic centimeters, more refined stone tool technologies, and possibly the beginning of more complex social behaviors. Homo erectus, appearing around 1.9 million years ago, represents a major leap forward. These were the first hominins to look truly human in body proportions, tall, with long legs adapted for efficient long-distance walking and running. Their brains averaged 900 cubic centimeters, well over twice the size of Australopithecine brains. They manufactured sophisticated stone tools using techniques that required planning and foresight. Most remarkably, they controlled fire, one of the most important technological breakthroughs in human evolution. Fire provided warmth, protection from predators, light after dark, and allowed cooking, which made nutrients more bioavailable and reduced the time needed for chewing and digestion. This freed up energy that could be invested in even larger brains. Homo erectus was also the first hominin to leave Africa, dispersing across Asia and reaching as far as Indonesia and China by 1.5 million years ago. This expansion demonstrates remarkable adaptability. These populations had to survive in environments very different from African savannas, including seasonal temperate forests and cold grasslands. They did so without significant biological adaptations, relying instead on behavior, tool use, and likely some form of clothing or shelter construction. This represents a fundamental shift in how evolution operates. Cultural adaptation was beginning to supplement and eventually outpace biological adaptation. Between 700,000 and 300,000 years ago, new hominin species appeared. Homo heidelbergensis emerged in Africa and Europe, with even larger brains averaging 1-200 cubic centimeters, approaching modern human levels. They hunted large game using wooden spears, built structured shelters, and possibly had some form of language or complex communication. From Homo heidelbergensis, two lineages evolved: Neanderthals in Europe and Western Asia, and Homo sapiens in Africa. Neanderthals deserve special attention because they represent the closest evolutionary cousin we have. They evolved between 400,000 and 300,000 years ago, perfectly adapted to the glacial environments of Ice Age Europe. They were stocky and muscular, built for conserving heat in cold climates. Their brains were as large as, or even slightly larger than modern humans, averaging 500 cubic centimeters. They were sophisticated hunters who used complex stone tool technologies, controlled fire, built shelters, wore clothing, and cared for injured group members. They buried their dead, suggesting some form of symbolic thought. Recent evidence indicates they created art, made jewelry, and possibly had symbolic culture comparable to early Homo sapiens. Homo sapiens, our species, evolved in Africa around 300,000 years ago, though the exact location and circumstances remain subjects of research. Early Homo sapiens looked somewhat different from us, with more robust skulls and faces, but were fundamentally modern in body and brain. Between 100,000 SAS and 70,000 years ago, something remarkable happened in Africa. Archaeological sites show an explosion of symbolic behavior, complex tools, art, jewelry, long-distance trade networks, and evidence of sophisticated language. Scientists call this the behavioral modernity transition, though it likely wasn't a single event, but rather a gradual accumulation of cultural innovations. Around 70,000 to 60,000 years ago, groups of Homo sapiens left Africa and began spreading across the globe. They reached the Middle East, then split into multiple dispersal routes, one moving through Asia to Southeast Asia and eventually Australia by 65,000 years ago, another moving through Central Asia toward Europe. They encountered Neanderthals in the Middle East and Europe, and another hominin species, the Denisovans, in Asia. Rather than simply replacing these species, Homo sapiens interbred with them. Most modern humans outside Africa carry 1 to 4% Neanderthal DNA, and some Asian populations carry Denisovan DNA. We didn't just replace our evolutionary cousins, we absorbed them, incorporating their genetic adaptations into our own lineages. The global expansion of Homo sapiens is unprecedented in hominin history. By 45,000 years ago, they had reached Australia, requiring ocean crossings that necessitated watercraft, the earliest unambiguous evidence of human seafaring. By 30,000 years ago, they had spread across Europe, displacing or assimilating Neanderthal populations. By 15,000 years ago, they had crossed the Bering Land Bridge into the Americas, spreading from Alaska to Tierra del Fuego in just a few thousand years. By 3,000 years ago, they had colonized the remote Pacific Islands, navigating thousands of miles of open ocean using sophisticated sailing technologies. Humans became the only large mammal to naturally inhabit every continent except Antarctica. This global colonization was enabled by an unprecedented reliance on culture and technology. Unlike other species that adapt to new environments through biological evolution over many generations, humans adapted culturally within single lifetimes. Moving to a cold environment, develop better clothing and heating technologies. Moving to a coastal environment, develop fishing techniques and boats. Encountering new prey, develop specialized hunting strategies and tools. This cultural flexibility allowed Homo sapiens to occupy more diverse ecological niches than perhaps any other large mammal in history. Here's the truth that most people never realize. The Cenozoic Era never ended. We're not looking back at ancient history from some fundamentally different world. We are living in the Cenozoic right now, at this very moment. Every breath you take, every landscape you see, every animal you encounter, all of it exists within the context of the geological epoch that began when that asteroid struck 66 million years ago. The mountains outside your window were pushed up by tectonic forces that have been operating throughout the Cenozoic. The climate patterns that determine your weather are products of ocean currents and atmospheric circulation established during this era. The plants and animals around you are descendants of the survivors and inheritors of the post-dinosaur world. And you yourself, you are a Cenozoic organism, a product of mammalian evolution that has been unfolding for 66 million years. Understanding this isn't just academic. It fundamentally changes how we see ourselves and our relationship to the planet. We live specifically in the Quaternary period, which began 2.6 million years ago and encompasses the Pleistocene epoch of ice ages and the Holocene epoch, which started just 11,700 years ago when the last glacial period ended. Some scientists argue we've entered a new epoch called the Anthropocene, the age of human influence, though this remains debated. Regardless of terminology, the point stands. We inhabit the same geological era that witnessed the rise of mammals, the formation of modern continents, and the evolution of intelligence itself. The Cenozoic isn't over. We're simply living in its most recent moments. This perspective is humbling and empowering in equal measure. It means that the geological and evolutionary forces that shaped the past 66 million years are still operating. Continents are still drifting. GPS measurements show that the Atlantic Ocean widens by about an inch per year as North America and Europe continue to separate. Africa is slowly splitting apart along the East African Rift, a process that will eventually create a new ocean basin millions of years from now. The Himalayas continue to rise as India plows into Asia. These movements seem imperceptibly slow on human timescales, but they're as active today as they were when Antarctica separated from South America, or when grasslands first began their global expansion. Climate is still changing, though now at rates that dwarf natural variability. The glacial-interglacial cycles that characterize the Pleistocene haven't stopped. We're currently in an interglacial period that, under natural conditions, would eventually give way to another glacial, advance tens of thousands of years from now. But human activities, particularly the burning of fossil fuels and the release of greenhouse gases, have disrupted this natural cycle. Atmospheric CO2 levels now exceed 420 parts per million, higher than at any point in the past 3 million years. Global temperatures are rising at rates not seen since the Paleocene-Eocene thermal maximum 56 million years ago, and we've discussed how dramatically that event transformed the planet. Evolution continues as well, though it's increasingly influenced by human activities. Species are adapting to human-modified environments. Urban pigeons, rats, and cockroaches are all products of evolution in human-dominated ecosystems. Some species are evolving in response to climate change, with migrations patterns shifting and breeding times adjusting to match changing seasonal cues. But the overwhelming trend is extinction. Species are disappearing at rates that rival the great mass extinctions of the geological past. The megafauna that dominated the Pleistocene, mammoths, giant sloths, saber-toothed cats, vanished between 50,000 and 10,000 years ago, coinciding with human expansion and climate change at the end of the last ice age. Today, remaining megafauna like elephants, rhinos, and great apes face existential threats from habitat loss, poaching, and climate disruption. The parallel to past Cenozoic events is impossible to ignore. The PETM, triggered by massive carbon release and resulting in global warming, caused extinctions and ecosystem disruptions that took hundreds of thousands of years to recover from. The cooling trend that led to Antarctic glaciation transformed the entire planet's climate and ecology. The grassland expansion restructured terrestrial ecosystems on every continent. Each of these events demonstrates that Earth's systems are interconnected. Changes in one component ripple through the entire planetary system. We're conducting a similar large-scale experiment right now, releasing carbon at rates that far exceed even the PETM, and the consequences are unfolding in real time. But the Cenozoic perspective also provides hope because it demonstrates Earth's resilience. Life has survived every challenge this era has thrown at it. Devastating climate shifts, sea level changes, habitat transformations, and yes, even past periods of rapid species loss. The biosphere has an extraordinary capacity to adapt, reorganize, and eventually recover, though recovery takes time measured in millions of years, not human lifetimes. The question isn't whether life will survive the Anthropocene. It will. The question is what form that life will take, and whether humanity will be part of the recovery story. Understanding our place in Cenozoic history also helps us appreciate the remarkable nature of the present moment. We live in an interglacial period, a brief warm interval between ice ages. For the past 11,700 years, Earth's climate has been remarkably stable by Pleistocene standards. Temperatures haven't swung wildly between glacial and interglacial extremes. Sea levels have remained relatively constant. Monsoons and rainfall patterns have been predictable. This stability enabled the development of agriculture, which began independently in several regions around 10,000 years ago. Agriculture allowed permanent settlements, which grew into cities, which developed into civilizations. Everything we call history, the pyramids, the Roman Empire, the Renaissance, the Industrial Revolution, the Digital Age, all of it happened during this single interglacial period, a geological eye blink in the context of the Cenozoic. This stability is the exception, not the rule. For most of the Pleistocene, climate oscillated violently on timescales of thousands to tens of thousands of years. Our ancestors survived those fluctuations through behavioral flexibility and technology, but they couldn't develop complex civilizations because the environmental foundation kept shifting. We've been extraordinarily fortunate to live in a period of unusual climate stability. Disrupting that stability carries risks we're only beginning to understand. The Cenozoic also teaches us about the power of long-term thinking. The processes that shaped this era, continental drift, mountain building, climate evolution, biological innovation, operate on timescales of millions of years. Yet they determine the conditions of the present. The coal and oil we burn are products of Cenozoic forests and marine organisms. The fertile soils that feed us were created by millions of years of plant growth, death, and decomposition. The biodiversity we depend on is the product of 66 million years of evolution, adaptation, and radiation following the dinosaur extinction. We're inheritors of deep time, beneficiaries of processes that began long before our species existed. This perspective demands that we think beyond immediate concerns and consider our actions' long-term consequences. The choices we make today about energy, about land use, about conservation, about climate will echo through the remainder of the Cenozoic and beyond. If we cause mass extinctions, those extinctions create evolutionary voids that take millions of years to refill. If we destabilize climate systems, those systems may take thousands or tens of thousands of years to restabilize. We're not just affecting the present, we're shaping the future trajectory of life on Earth, potentially for millions of years. But here's the remarkable thing. We're the first species in Earth's history capable of understanding these deep time processes and potentially managing our impact on them. Every other organism responds to environmental conditions through evolution and adaptation, processes that take many generations. Humans can study the past, understand the present, and plan for the future. We can see the patterns in geological records and recognize when we're pushing the planet toward tipping points. We can develop technologies that reduce our environmental impact. We can make conscious choices about how we interact with the planet. This cognitive ability, the product of 66 million years of mammalian brain evolution, gives us both tremendous responsibility and unprecedented opportunity. The Cenozoic story is ultimately one of resilience, adaptation, and transformation. It's the story of a planet recovering from catastrophe and reorganizing itself into new patterns of complexity and beauty. It's the story of mammals seizing an opportunity and diversifying into every possible niche. It's the story of intelligence emerging from evolutionary pressures and eventually developing the capacity to understand its own origins. It's an unfinished story, still being written with each passing moment. And you are part of that story. Not as a passive observer, looking back at ancient history, but as an active participant in an ongoing saga that stretches back 66 million years and forward into an uncertain future. The Cenozoic Era shaped you, your mammalian biology, your primate cognition, your human consciousness, and now you have the opportunity to shape the Cenozoic's future trajectory. What we do in the coming decades and centuries will determine how this chapter of Earth's history unfolds. What species survive, what ecosystems persist, and whether humanity's time as a dominant force on this planet is measured in thousands of years or millions. The secret age after the dinosaurs isn't really secret at all. It's been hiding in plain sight, written in the rocks beneath our feet, encoded in the DNA of every living thing, visible in the landscapes around us. The Cenozoic Era is our inheritance, and our responsibility. Its story is our story, and its future depends on the choices we make today. If this journey through deep time has sparked your curiosity about Earth's incredible history, don't let it end here. Subscribe to the Sleepy Cosmoz for more explorations of the science that shapes our universe. Hit that notification bell so you never miss our next adventure through space, time, and the wonders of our cosmic home. Share this video with anyone who loves learning about our planet's remarkable past. And remember, you're not just watching history, you're living it right now in this extraordinary moment of the Cenozoic Era. Let's make it count.